Hello, welcome back to the second part of lesson 8.1, kind of introducing all the pieces and parts to hypothesis testing. The next little piece I'd like to go over is the two distributions that we're going to be using. So just like in the confidence intervals, when we're talking about means and quantitative data, we're going to be using the t-distribution. With mean of the sample means, and then your standard error is taking the standard deviation and dividing by the square root of n. Okay, and it's mainly just thinking about we're using the t-distribution. Then if we're talking about proportions, we're going to be using the z-distribution. The cool thing is in ALEKS, there is under the calculator to find your critical t value and z value. It's in the calculator. There's just a button, and then you put your little alpha. So that's or alpha divided by 2, which is awesome. But when you're on the final exam, you won't have access to ALEKS, so you'll have to just use either the little table that I've shown you in the formulas packet that you can print from Canvas, or typing in how I've taught you in the notes using inverse CDF to find your critical T and critical Z. So let's look at example 11, just a few examples to learn a little bit more about our population. So example 11 says, which distribution do you use when the standard deviation is not known and you are testing one population mean? Assume your sample size is large. And so that's going to be the T of alpha and degrees of freedom. Example 12, you are performing a hypothesis test of a single population mean using a student's T distribution. What must you assume about the distribution of the data? And we're going to assume that it's normal. And sample size is large enough, because we're still using the T distribution. Remember that, because it's population mean. Example 13 says, you're performing a hypothesis test of a single population proportion. You find out that NPQ is less than 10. What must you do to be able to perform a valid hypothesis test? And remember, this is sufficing to serve for the normality piece in the central limit theorem. So you're going to have to increase your sample size. If you increase your sample size, then your NPQ will be bigger than 10. So we're going to run a little experiment, and we're going to use the data from my class. It's I had all of my students in class roll a 6-sided die 12 times, and they tallied the number of 5s that came up on the die. And then we counted those. So we had 0 students. You can tally this with me. They had 0 students that didn't get any 5s. There were 6 students that rolled 1 5 out of the 12. There were 3 students that rolled 2 5s, 4 students that rolled 3 5s, 3 students that rolled 4 5s, 1 student that rolled 5 5s, and then we had 0, 0, 0, 0, 0, 0. And mysteriously, there was a student that rolled 12 5s. So this one seems a little atypical, and so does this one. I mean, out of the 12 rolls, she got 5 5s, and he got 12 5s. So we're wondering if ourselves, what was the outcome? Most reasonable, except that one right there. And we could, I mean, it says the same reason, we could say maybe it was a fluke, right? We really only came up with 2 good reasons. Maybe it's a fluke, or maybe that student had a weighted die. And truth be told, that student did have a die. I have a special die that has all 6 sides have 5 on them. So it works out. It works out for us. How could we decide if it's reasonable or not? So we can do this in 2 different ways. We've learned with quantitative data this semester, we've learned that if a value is more than 2 standard deviations away, right, we consider that unusual. Or with qualitative data in our probability section, we learned that anything that is less than 5% likelihood, we said was also unusual. So we could find out the likelihood of rolling using our binomial distribution and N and P, right? So N was 12 rules, and the probability of getting a 5 is 1 out of 6. And then we looked at when X equals to 12, when you get all 12 of those rules is a 5, and that probability is very, very close to 0. So definitely less than 5%, like we've been looking at. So we would definitely say that this is unusual. So when we are running hypothesis tests, we have to decide what rare events are so that we can conclude the right thing. So it says, suppose you make an assumption about a property of the population H0, then you gather data randomly. If the sample has properties that would be very unlikely to occur, if the assumption is true, then you would conclude that your assumption about the population is probably incorrect. Remember that your assumption is just an assumption. It is not a fact, and it may or may not be true, but your sample data are real, and the data are showing you a fact that seems to contradict your assumption. So we're going to do this in 2 different ways this semester. It says use the sample data to calculate the actual probability of getting the test result called the p-value. Okay, the p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given example. Okay, so this is important to know, this description of p-value. The probability, the p-value is a probability of this particular outcome happening given that the null hypothesis is true. So we're also going to use this probability and also using z-scores to decide if we are in a danger zone. So let's look at example 14. It says a normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. So I'm just giving you this information. We have no data, but it says our null hypothesis is that the mean is 12. We think that it's greater than 12, right? That's what we're wondering. This is what we're testing. The p-value comes out to be 0.0013. Let's just draw a graph what that would look like. So we're going to be able to draw what we're looking at. So I'm going to draw them here. I'm going to draw that the mean is greater than 12. And that p-value is right here, 0.0013. So unlikely, it's less than 5%. So, statistical significance is another way to describe that something is unusual. When observed results from a random sample are very unlikely due to chance if the null hypothesis were true, we reject the null hypothesis. So using the classical approach is when we consider very unlikely the sample statistic is too many standard deviations from the parameter assumed of the null hypothesis. So this is where we're going to look at our z-score. And if it is further than the absolute value of our critical T of alpha, or, well, this one would be our Z of alpha, or if our t-score or t-value, right? We're using t when we're talking about the quantitative data and z when we're talking about qualitative data, is further away than our critical t-value, then that's one way that we can say something is unusual. Up to this point, we've just been using the two standard deviations, but now we're going to be using, depending on the situation, we're going to be using different critical t-values. Or we can use the p-value approach. And the p-value approach, we consider something very unlikely if the probability or p-value of obtaining the sample result given the assumed null hypothesis is extremely low. So if the p-value is less than alpha, then we reject. Okay. So I have it here. I just kind of summed it up here. If our p-value is less than alpha, then we reject H0. If we're not given an alpha, then we use alpha equal to 0.05. Or or if, like I said before, if our t-score is further away than the absolute value of our critical t-value, or if our z-score is greater than the absolute value of our critical z value, then we also reject. So we're going to put all of our steps together. The last two steps are step 5 and step 6 of a hypothesis test. And step 5, how we come up, after we come up with step 5, it directly tells us what we're going to write for step 6. So if we reject the null hypothesis, we're going to say reject H0, and then we're going to exactly write, there is sufficient evidence to support the claim that, and we're talking about H1. So step 5 is only about H0. Once we make that decision, then we write step 6 only talking about H1. Those are important pieces. And notice we never say we accept H0 or do not accept. It's always reject H0 or do not reject H0. If you do not reject H0, then there is not sufficient evidence to support H1. Okay, so do not reject H0, there is not. So not and not go together. We're going to get lots of practice with this. Okay. It's a Boy Genetic Labs claims their procedures improve the chances of a boy being born. The results for a test of a single population proportion are as follows. I'm giving you that they think it's 50%, but the genetics labs claims that it's a higher than 50%. We're testing at a 0.05 alpha, so a 99% confidence. And the p-value, after some data, you don't know the data because I'm just giving you this, we're saying the p-value after some data is 0.025. So step 5 would be to compare the p-value on the left, is what I always do, to my alpha on the right. I just always do it on the p-value on the left, alpha on the right. And the p-value is 0.025 and the alpha is 0.1. Now, because my p-value is larger than my alpha, we do not reject H0. We only reject when our p-value is less than our alpha. And so, because we do not reject H0, there is not sufficient. We're going to write that out here. So step 6 says, there is not sufficient evidence to support the claim that the procedure improves the chances of a boy being born. Okay, so I do want to make sure I hit home on this. So I said if the p-value is less than the alpha, then we reject H0. For the classical method, we've got our t-score, our t-value that we're going to calculate, and our z value. We call that the test statistic. Now, we can think of it as we're going to come up with our critical z or t-value here, and we're going to mark that. This would be a two-tailed. A two-tailed, you have one on the left and one on the right. We take our alpha and divide it by 2. If it's only on the left, all of our alphas on the left. If it's only a right-sided, all of our alphas on the right side. We're going to do several in lesson 8.3. But we're going to mark our critical t-value. And then any test statistic, t or z, that falls outside of those critical t-values, we're going to reject. You don't reject what is in here. So far this semester, we've said 2 has been our break point, right? We said anything outside of 2 standard deviations is where we reject. Now we're going to make decisions based on the manufacturer's choice or the FDA. They decide like what critical t-value will say that something is an unusual event. So catch me back for lesson 8.3, and we're going to put everything together and actually run some hypothesis tests.